All right, so now we're going to talk about power series and the interval of convergence. Now, as I looked through this, guys, it was pretty wordy. So I'm actually going to go back to my own notes and hopefully it'll show here. But I created sort of my own notes on here in Google Keep, and I'm just going to show you sort of just the very basics of it. I'm going to attach a video for this. The guy actually does a really great job of giving you several examples of how this works. But basically, a power series in X can be viewed as a function of X, right? So that's kind of important. It's a function of X. So notice that as opposed to other series that we've dealt with so far, this one has some kind of X function in it. Okay, so that's how I was able to determine what's a power series and what's not. Now, that might be the very basics, all right? So this is not necessarily the gospel here. So the center of the power series is centered at C, all right? So notice that X minus C is right here. So if you just set that inside equal to 0, then X is equal to C. So when we talked about the center of the power series, that's what we're talking about, okay? So now to determine the radius and interval of convergence, we're going to have to use a ratio test when it comes to power series. And then three things are going to happen when you use the ratio test, okay? The first thing that could happen with the ratio test is that you get 0. Now, according to the ratio test, if you remember, if the limit of the absolute value of a of n plus 1 over a of n is equal to 0, anything less than 1, then it's, if it's greater than 1, it was divergent, all right? And if it was less than 1, it was good. So if you have that, so this is the first scenario. If you take the limit and you get a 0, then what that means is that since 0 is always less than 1, then for all x's, it's basically going to be convergent everywhere. And that's what this means, all right? So you're going to be convergent everywhere. So the ratio of convergence is also going to be infinity, all right? So now for the second scenario here, and I know that I'm saying things that you may not understand, but hopefully after we do a few examples, you'll understand it. On number 2, if you use the ratio test and you get infinity, now we know that infinity is definitely not going to be greater than 1, right? It's not less than, infinity is not less than 1. So what happens there is that the series is only going to converge, the power series is only going to converge at the interval x is equal to c. And again, I'll give an example of that, right? So that one may not make a whole lot of sense until I do it. So just hang in there. And then finally, you have what's basically going to happen the majority of time when you're using the power series test, or the interval of convergence for the power series. I don't know if that's called a series test or not, but essentially what would happen there is you would get some number, okay? You basically would end up with something that looks like this. And again, I'll give you an example of that here in just a second. So once you have that, okay, then you're basically going to notice that when you have an absolute value, you're going to basically solve for x, right? You're going to put a negative r here, a positive r here. You have an interval, and this is going to be your interval. So my interval of convergence is this. Now my radius, okay, an easy way to do that is to figure out your interval of convergence, like the distance basically between this value and that value, whatever that may be, and then you're going to divide that by 2. So it's basically the distance of the radius. This is kind of lagging a little bit. The distance of the interval divided by 2. Okay, so I'm going to get out of here because it seems like this is struggling. So now let's go ahead and let's go to a few examples of your notes. All right, so again, everything I just said is basically everything they say here. And let's go to example 4. All right, so in example 4, what we're going to do here is that, so first of all, you got to recognize that's a power series. All right, so it is, and to figure out the radius of convergence and the interval of convergence, you're going to have to do the ratio test, right? The ratio test is what I wrote on this note. So let's go ahead and switch my color to blue. Let me switch my colors to blue, and let me move away from the bedroom, or sorry, from my living room so my wife can cook. Close the doors so the dogs can't get in. Okay, so let me get accustomed here. My apologies. So this is what we're going to do, right? So the ratio test says that you're going to have the limit, or that shouldn't be equal to. Let me get rid of that equal to. The ratio test works like this. basically going to add 1 to the n. So everything that has an n, you're going to add a 1. And then you're going to divide that by this. But when I divide that by that sequence, if you will, that's going to keep changing and flip, right? So this is going to be flipped to this. And of course, is the absolute value of all of that. So here, let me go ahead and try to simplify this just a little bit so you can see what I'm about to do now. X minus 2 n plus to the power of n plus 1 could be rewritten like this if I wanted to. And to the power of 1 here. And I'm going to go ahead and put the x minus 2 to the n over here. And then I'm going to separate like that. It may look, you may not understand why I'm doing that right now, but just hang in there with me. I'll show you why. All right, so now I have, let's see, n over n plus 1, and I think that's it. All right, so notice that this and this is going to cancel, okay? So what I end up with is the limit as n goes to infinity of, I'm going to write it in a strange way, so hang in there. I'll write that like this. Now, I'm not going to write that like that every single time, but I want you to understand where I'm getting this from. Now, because the limit only has to do with n, all right? I can actually rewrite this as, well, I can go ahead and just take the limit, right? The limit of this, hopefully you can see that this is 1. So I can rewrite that as 1 times x minus 2. Now this right here needs to be, for it to converge, to figure out the interval of convergence, I have to set that, or I have to put it as less than 1, okay? Because that's how the ratio test works. So what I'm going to do from here is I'm going to solve here. So remember, when you have an absolute value, you essentially, and don't copy this down yet, you essentially would write the same thing, but you would have them, you switch the inequality, you make that negative, but in reality, what you could do that would be faster, that would be the same thing, is write it like that. All right, so notice how I switch the signs on the 1, so you have a negative 1, a positive 1. And this sign, even though it looks like it's the same as this, it's not, okay? So again, if you have more questions about how I did that, please let me know, because I don't want to spend forever on it. So I'm going to add 2 to each side. So my interval is going to be x is less than, or 1 is less than x, which is less than 3. All right, so basically my answers are between 1 and 3. Now, my radius of convergence, all right, this is almost my interval of convergence. So in order for me to figure out the rest, and I'll come back to the radius in just a second, is I'm going to have to test the endpoints to figure out if those are also part of my interval of convergence. So what I'm going to do here is I'm going to plug in a 1 for x. So I'm going to test. Let me write it like that. I'm going to write test. Let's see, x is equal to 1. All right, so when I plug in a 1 here, I would end up with 1 minus 2. So this would be the sum between 1 and infinity of negative 1 to the n power over n. Now, hopefully you can see that this is actually, and you can use the alternating, so this is the part that kind of stinks for you guys, which it did for me. I can use the alternating series test, all right, where I basically compare it, and I'm going to write it here basically to 1 over n. Okay, so basically I don't pay attention to the negative 1. I had a little bit of a hiccup with my technology. It cut me off for 10 minutes. But anyways, now we're back. So What I was saying on the first test is that you have to prove that when you plug in a 1, remember right here, all right, and you would get this right here. You have to figure out if that converges or not. Now, in this case, that is going to converge. Okay, so what that means to you is that in the interval of convergence, that is going to be part of it. Okay, so that's the 1 is included. Now, as far as the 3 goes, if I plug in a 3 here, notice that I have a 1 to the n power over n. Now, 1 to the n power is basically, that's not going to change, right? Doesn't matter what you raise that. 1 to the first is 1, 1 to the second is still 1. So this is the same thing as this. Now, as far as that goes, excuse me, the 1 over n is the harmonic motion, which is also called, it's also a p series, but the harmonic or the harmonic series, excuse me, harmonic p series does not converge. It diverges. All right, so what that means to you is that this right here, the 3 is not going to be included. So this right here is going to be the interval of convergence. Now, to figure out the radius, you have to just basically look at the distance between 1 and 3. I don't care if the 1 or the 3 are included, doesn't matter, right? So the distance between 1 and 3 is 4. So the radius is going to be the total distance and the interval, and you're going to divide that by 2. So the answer is 2. Okay, so that's the radius of convergence. Right, well, let's go ahead and move on to the next one. I think it has some of those examples that we're talking about. So most of your homework is going to be like what I just showed you on A. Okay, now there is sometimes like on B. All right, again, this is a power series, and I'm trying to figure out if this is, well, I'm trying to figure out the radius of convergence and the interval of convergence. So I'm going to take that to infinity. I'm going to do the ratio test. So I have n plus 1 factorial x to the power of n plus 1. And on this one, since it's not really a fraction, all I can do is just divide this by the original sequence right there. And I'm going to try to simplify that before I can take the limit. Now, sorry if I write too much work on this. I feel like I have to. Okay, so I have n plus 1 factorial. It can be rewritten as n plus 1 times n factorial. And it looks like right. And then x to the n plus 1 can be rewritten like this. Now I have n factorial, and I have an x to the n. This is going to cancel this. This is going to cancel this. So essentially what I have is the limit as n goes to infinity of n plus 1 times x. Well, what's going to happen is that this right here is going to be infinite. There's no other way around it, all right? So that's going to be infinite. So what that means is, because when you have this right here, you're going to have an infinity is going to be x like that. Okay, so this whole thing is going to be infinite. So this is what I'm going to explain why there is basically one point where it converges. All right, so if I want to make this, has to be I have to make this less than 1. Okay, now I know that looks weird, right? So just hang in there with me. No matter what I pick for x, that's always going to be greater than 1, except if x is 0. All right, so if x is 0, okay, if x is 0, then I would have infinity times the absolute value of 0, which is 0, and 0 is less than 1. So what I'm trying to say on here, let me find the best way to write this. Example 4. All right, this is the only place where this is going to converge. Okay. So in terms of the radius of convergence, is going to be 0 because there's not even a ratio for you to do, right? So you basically have 0 divided by 2. So the radius of convergence is that. And I guess this would be more or less your interval of convergence would be right there, okay, which is nothing. So it only converges. So let me write that just to make sure we're on the same page. So it only converges when x is equal to 0 in this case. All right, so let's go ahead and move on to C. Okay, so on C, what we're going to do now is let me fold this over. We're going to do this ratio test again. This is a power series. So now I have, let's see, -1 to the power of n plus 1, x to the power of 2n. Oh, this is going to be weird. So don't write this yet. So this is going to be n plus 1 here, plus 1. So this is going to give me 2n plus 3, all right, if I distribute this and I add that 1, all right? So just to save us a little bit of time, I'm going to write this as 2n plus 3. Let's see, over, by the same reasoning, this is going to be 2n plus 3 factorial. Then we're going to divide this by the original function here, or original sequence. When I divide, I'm going to flip that, right? So I have 2n plus 1 factorial divided by -1 x to the power of 2n plus 1. All right, so let's go ahead and try to simplify this a little bit. Notice that I'm just splitting up those powers like that. And then 2n plus 3 factorial, I can write it like this. So bear with me here. It's just takes a little bit. All right, so hopefully you can see what I did there. I'm just splitting everything up. Now, this right here is going to cancel with something. Did I leave something out? Yep, I left something out. I left this n right here. All right, so now this will definitely then cancel with this. This will cancel with this. This will cancel with this. Okay, and then now, let's see what I have left. Do I have a 1 over x? Is that right? Oh, no. Then this x reduces this to x squared. All right, so this is going to be the limit. Sn goes to infinity. I'm going to join all the n terms together. So in this case, I have a -1 over 2n plus 3, 2n plus 2. And all of that times the absolute value of x squared. Now, listen, sometimes when you look at the key, they'll just write this a positive 1, which they can. They could have factor out, right? Because if you just take the absolute value of -1, you would get a positive 1. Now, in this case, it's not really going to matter for the limit, because the limit of this right here is going to be 0. Okay. So what I end up having here is 0 times the absolute value of x squared. Now, think about it. Is there any number that you can plug in here? Remember that in order for the ratio test to work, it has to be less than 1, right? Well, this is always going to be less than 1 because if I multiply 0 times any number that x could be, this is always going to be 1, correct? Excuse me, that's always going to be 0 on this side. So what does that mean? Well, what that means is that this is going to be convergent everywhere. Okay, so it's not only going to be convergent at one point or at a certain interval, but it's going to be um, convergent absolutely everywhere. Okay, so here's a convergent interval if you want to write it like this. And then the radius will also be infinity. Oh, so it's infinite. Okay, so hopefully that makes sense to you. Okay, now make sure that as you're looking at the homework, don't just ignore and be like, oh, yes, yes, I think I can see that. All right. I did have to look at some videos, and as a matter of fact, I had to look at other videos that I will probably attach on here for me to figure out how to do some of this stuff because it wasn't very apparent at the beginning, but hopefully that what I broke it down kind of helps you out, okay? So again, take a look at the video that I attached to this. You don't have to obviously do any of the examples that he does, but he does way more examples than I do, and I think they're very, it's a long video, but I think he does a great job. Right, until next time, guys.